Sorry for the technical issues, and finally I can present my ongoing project, higher order cumulants near to the critical point from electrodynamics, which I'm performing as a part of my graduate studies in the University of Houston. And I want to say thank you for hosting me here for a month. It's a very nice lab, and I like people here, and I like the Western here much more. So the start is pretty trivial. This is a well-known sketch of the phase diagram, and the answer why, in general, we are interested in the studies which are performing is the answer to the question why is a sketch. Because, unfortunately, in general, there are no such analytical approach which would give us the opportunity to map all the phase diagram. Since we cannot, in general, solve the QCD, like we can solve some other theories, like electromagnetic theory, for example, we cannot build the very, very simple explanation for many questions here, like, for example, what is the precisely these numbers here, where is the color superconductor region, where is the hadron gas region, and also the question which are interesting for me, at least now, is the existence of the critical point question. If it's there, and where it is. And that's why we need some approaches to understand what we can observe in the, for example, experiments. We can use the well-known from the statistics quantity called fluctuations. Fluctuations are very sensible to the equation of state nature, and that's why once you have the opportunity to study them, sometimes you can look deeper in the structure of the matter. So here you can see the first and well-known for me now after 3 years cumulant ratio called scaled variance, or omega as I call it here. And the upper plot shows you the van der Waals comparison with the Lennard-Jones comparison. Lower plot shows you the, the van der Waals phase diagram. And you can directly see that somewhere near to the critical point, the scale variance increased dramatically. However, this logic with partition function, which I'm sure well known to everyone, cannot be used that direct in the system which are not large enough, which have some kind of effects of the finite size, conservation, and so on. And that's why, in general, it's important to study them in the approaches like molecular dynamics, which gives you the direct insight of it. A few words about two different quantities, which also will be studied here, is the skewness and kurtosis. Skewness and kurtosis is the ratio of K3, K2, and K4, K2. And why they're interesting? There are two main reasons for it. First reason is purely practical, because from the start data, we cannot really get anything up to the higher of the fourth cumulant. So it's hard to get hyperkurtosis or K8, K2, whatever. So realistically speaking, if we want to compare it with something real, we need to study up to K4. Also, another reason is that these ratios are interesting because they're independent of volume, and also because, as you can see here on this plot compared to the previous plot, they are getting more and more sensitive to the criticality in the system. So we're getting a larger region where this quantity is sensitive to the existence of the critical point. So here's an example of the data. It's about, of course, cumulant ratios which will be different to my cumulant. Also, of course, they can be expressed to each other. So you can see here, as it was many times discussed, this behavior, especially in the, if you look the proton cumulant here, right? This behavior needs to be explained somehow, and that's a motivation for us to study our simpler model, because in our model we know that critical point exists, and we can compare the case to the real case of experiment, but people don't know it. A few words about the difference between the theory and experiment, because, of course, once we're talking about something that can be measured, it's very important to understand where we are here. Once we work with the theoretical approach, in general, we have the homogeneous system. We can find the volume and define the density, the number of conserved charges or conserved particles, and of course we can work with the with no volume fluctuations. Also, in case of the experiment, unfortunately, usually it's impossible even to properly define such things because of many different parameters. So, for example, what we would define as density of the system, right, in the Hadron collisions. It's also the case that we can work only in momentum space in the case of experiment, and that's something that not always the case in the theoretical approach, but fortunately in our approach we have some insights from it, and I will discuss it later. And one important thing here is that I put it separately, that both approaches need microscopic description of fluctuations, and that's what I said, that in general that's something that can be easily forgiven when we work with the partition function and the canonical ensemble formalism. We should remember that it's important. A few words about our interaction potential. It looks pretty trivial in the sense that we have this well here and the whole, like the effective radius of interaction. But why we choose this potential? This potential is chosen due to two pretty simple but important reasons. First reason is that because it's known to have the 3D Ising class of universality, which we expect to have also in the QCD, if, of course, critical point exists. And another reason is this phase diagram, which is nicely mapped here. And the reason why it mapped so nice is because this potential is studied for many years now, maybe I think more than 40 years. So we don't need to map it ourselves to, not to get somewhere like inside of the gas liquid region when we try to study the 1.4 here, the upper critical temperature. So that's the practical reason why we choose this potential. A few words about the simulation setup. We use the 400 equations, Newtonian equations of motion, which gives you connection between the potential and the radius vector of the particle. We use it to three densities: the small density, middle density, or near critical density, better to say, and large density. You can see them also here. We perform the large statistics of 2 million events, and it's very important because without large statistics we cannot get any reasonable precision of our measurements for even for schemas, so K3, K2. And we initialize each events with random initial condition, which is important for the independence of the measurements, and run each simulation for long enough time, where long enough time is something that we need to find from which we did. Anyway, calculate the observables as event by event ensemble average, which is more realistic, and it seems to me that it's also easier computationally. And yeah, this code is in open source, so if someone interested to review it, I can give you the link. Anyone can do it if you're interested. Here, the first important result which you obtain. So I wrote it cumulative calibration, but what you can see here? You can see here our scale variance schemas and kurtosis as a function of the time of simulation, which means that in each of this time we perform the snapshot of the system and do it for 2 million times. That's how we obtain these points on this line, and we can clearly see that if our time is too small, let's say 5, we are far away from the equilibrium result here. The question which naturally we can ask is if this result ergodic, and that's something that we try to understand for scale variance, from schemas and kurtosis, but we check that for scale variance this result is ergodic. So it matches the time averaging.
What's the unit of time here?
Excuse me?
What's the unit of time for me?
It's this reduced time unit, which can be connected to the parameters of interaction. So the potential have the potential well, or potential depth, and the radius, effective radius, right? So you can renorm the time velocities, the lengths on them. That's why we're working in the dimensionless variables. The dimension can be restored, but for this you need to know which substance you simulate. So you need to know the interaction parameters.
So do you have freeze out here in the simulation?
Excuse me?
Do you have the freeze out in this simulation?
It's not really that we simulate without. Our system is simpler than this. We say that
it's contained in a box with periodic boundary conditions. So it doesn't expand.
Oh, I see.
Yeah.
It's not here by operating.
No, it's a box.
Oh, I have a suggestion. So instead of just eyeballing this figure, you can add some analysis of autocorrelations. Maybe it will it's just very interesting to.
I agree, but does we have autocorrelation really increased ensemble average?
Well, here
I don't think so.
autocorrelations increase with time, so this is just a way to.
No. So this is I understood your point. So you're wrong in sense that this is ensemble averaging. So it's not a system which simulates for a long time. We have a snapshot at, let's say, 25, and we do this small time 2 million of times, which means that our system not simulate for long, like it is in the in the simulations which happens with time averaging. So
You have time here.
yeah, so I mean, I think we can do what you're saying, but it will be small. That's my point. I don't think that correlation play a role in this case. They should play a role in the time averaging.
Do you have an analytical solution for this?
For this, no. So this is a result of the molecular dynamics simulation, and it shows the thermalization time of our system, which interacting gas in the box's boundary condition. So yeah, unfortunately, there's no opportunity to integrate it out.
You have analytic fit, right?
Yeah. Okay. But it's just decay and exponent. So we can find
But that's only in the critical region, right?
So this is not for every.
Monte Carlo,
Where
with
is
the molecular dynamics time evolution.
Yes. So these lines are results of the simulation. So basically, you just studied the given subensemble in our box and perform the averaging over each snapshot for 2 million. That's how you get the mean cumulants values, and then you found the K2, K1, K3, K2, and K4, K2, which is these three.
Maybe
values.
you already mentioned, but how do you place the particle when you start the dynamics? Like in
Randomly.
London.
So we perform, I probably should say, because I said randomly only for the coordinate space, but I need to notice that for the momentum space, we did the Maxwell-Boltzmann distribution for proper temperature. Also, this is simulation in the microcanonical ensemble, so temperature here is not strongly fixed. What is fixed is the energy, which we expect to be more realistic. And energy is proper energy which corresponds to the given temperature which you want to simulate. Yeah, and these three densities I provide here are all for the same temperature, which is 1.06 of the critical temperature. So it's slightly above to the critical temperature. That's why you can see that, for example, kurtosis is very small. Like it's very large negative, better to say like this, is a sign of the critical pole.
So the Lennard-Jones group.
Yeah, sure. The next interesting result, which you can see here, is the alpha dependence, where alpha nicely depicted here. So we have the subensemble in the coordinate space, which is basically this red particles you can see here. After 2 million events and averaging, you can obtain with normal precision, not too bad. You can see even for kurtosis, it's not terrible. You can really see the pattern here. We can obtain the three cumulants as a function of this alpha subensemble volume. And it's not very unexpected to see the huge signal for the blue line, which is the line at the critical density. And even this kurtosis here is minus 15, and it looks pretty large for such a small system of 400 particles. Unfortunately, the real kurtosis, which we estimated and will show in the future, that it should be much more negative. So basically, this value seems principally not Gaussian, because this red line is the ideal gas line, which means no interaction, which means the binomial distribution. Although this deviation, large deviation, is a clearly signal, it's still far away from the thermodynamic limit.
What is alpha?
Sir?
What is alpha?
Alpha is depicted here.
It's the fraction of the total. You have one box and then you look at a sub box, and the fraction of the size of the
Small fraction.
small volume, the large volume is alpha.
Okay.
Yeah, so to compare it with some kind of grand canonical expectation, we need to do some ensemble method of correction for global conservation. I mean, it's pretty, the formulas itself is pretty simple. Also, I want to make two comments here. First of all, it's about alpha definition. So, in general, alpha can be defined as was shown before, but these formulas are not connected to the definition. So, I prefer to say that alpha can be defined like this. And it can be shown that for the system in the coordinate space, it corresponds to the just volume fraction. Another comment which you want to notice is that this function here for the scale, for the skewness have the pole at alpha equal to 1 divided by 2. So this pole is not a real thing. It can be shown, for example, in the van der Waals model, which is analytical, that there are no such pole there. Also, the problem which you have in our system is that our results have the precision. It's not something analytical. That's why I will show the next results only up to 40% of the system, just because in the middle they blow up because of the non-zero precision. So you can see them here. This is our corrected for the global conservation three cumulants, and their behavior is expected. Although the problem which we obtain here is that how much is expected, right? We see that this red line, which equal to 1, is the non-interaction ideal guess. And we see that it deviates pretty much. But how much it should deviate in the grand canonical ensemble? It's a good question. And as you can see here, it should deviate much more. This black line is the virial estimation of the cumulants for the Lennard-Jones. Of course, virial estimation means that it's not the actual equation of state. But it's the best estimation which we have. I would say that it's probably something like lower bound. You can see the 3 points which I depict here. It's our actual result, and they're very far away, even for the scale variance. You see that it's like here's 2 and here's 8. So we are very far away from grand canonical ensemble.
Except large density.
Yeah. I mean, I'm not talking about critical density. Yeah, large density is everything suppressed, so it's pretty.
No, but that's important.
Yeah.
Size, right?
Well, then I would notice that also for the schemas, you can see that it's also already thermalized to the grand canonical. It's already flat. Why? Answer is pretty simple in this plot. It's because it's near 0. So there are nothing to approach. You just expected answer that it's very small, so it's easy to thermalize there. Which means basically that the formal distribution corresponds to our expectation. But what is important to see is this plot, because you see that it should be minus 1000, but it's just minus 50, which give us some kind of intuition how much our system deviates from ideal guess, and unfortunately it's not that much, which means that 400 particles have still a very large suppression at the higher cumulants, which, I mean, not really makes sense. Now a few words about another important quantity, factorial cumulants. Factorial cumulants is more sensitive for the n-particle correlation, and here you can see the factorial cumulant for the critical density. Naturally, the signal is large, because you see the signal is large for standard cumulants, they are connected, signal is large for factorial cumulants. Here, we want to ask a question, but if we want to explain something about the real experiment, then we cannot observe the whole baryonic system normally. We observe only charged part of system, like protons.
Hold on, in your third order cumulant on the previous slide, third order, sigma, the skewness. Your signal is very small, as it should be. Why is it now for the third order factorial cumulant large?
Well, because it's have K2 here.
It's also not correct.
Yes, yeah, okay, yeah. I should say that these factorial cumulants are not semi-ensemble corrected. This is right.
Okay.
But moreover, it's also the mathematical answer because it consists K2. And K2 is large. Okay, so that's why we want to study the charge conservation for the protons. And we perform 2 scenarios of this study. First call is a spin randomization, which means that we just randomly choose how to do the system each time for each event and average it over this randomly chosen events. This is shown at the work of Kitazawa that is good for the averages of collision more than 10 GeV. Another case, and the important part of this is that this case is kind of trivial because in the Adams Duck paper it was shown that I don't think I saw it there, but I think it's shown in the textbook also, that this relation should be true for this case. So basically, it's a simple power law for the multi-component system, how the factorial cumulants should scale for the part of system and the whole system. For the charge conservation, situation is more intriguing, and it is, because we choose a part of system to be charged, let's say just by numbers of particles, first half, for example, and we not randomize over them. We just study the fluctuations. Is this named to be charged part of system? And this is good for the lower energies, which is more interesting region, and it will give us some unusual result, which you can see here. So the dark blue line here is the whole system. Again, everything here is for critical density. I choose it to show because it's more instructive since the signal is largest here.
Just to clarify, whole system means all baryons. It's still a subsystem in coordinate space.
Yes.
When you say whole system, right? It's still a subvolume.
Yeah, but I mean, you have alpha, so it's the picture of whole
exactly.
system. Yeah. But of course, each measurement performed in subvolume because we have total number of particle conservation. So the whole thing is not fluctuate at all. So you can see here the blue line as the full baryonic line with the largest signal, but two other line corresponds to the two scenario which I discussed for the charge conservation. The pink line corresponds to the large energy isospin randomization, and it just as expected here 2 times, here 4 times, here 8 times smaller. So suppression is trivial in the sense that it's expected, but it's a good sanity check that everything works, that our system is not violate known things. However, for the orange line, charge conservation, small energies, you can see interesting behavior because, of course, signal is suppressed here and here as expected, but here it's suppressed that much that it almost matches the red line, which is the ideal guess. Which means that such case that we measure only charged particles might be explanation why we don't see any large deviation from the Gaussian result. Just because, unfortunately, they vanish out once we perform study not over the whole system, but charged sub-part of the system. Yeah, and the question that might be very relevant for this Rick observation is something that we discussed in thinking. Here you can see the normalized factorial cumulants or Zach ratios. And you can see here that they basically corresponds to the same plot which we had before. So just for the baryons, it matches the ideal gas at large alpha and starts from the some suppression because of the because of the alpha subvolume size. So maybe worth noticing here that for the higher cumulants on this Zach ratio, it's getting worse and worse to observe something deviation from the flat, so they all looks kind of the same. But maybe what is worth noticing here is that they, especially in this plot and this plot, the blue line and the orange line, which is baryons and charge conservation, they are matching. So there are no difference in it, which is not true for this plot. Orange and blue lines clearly different here. So this result is.
You mean the orange and the blue? Where's the orange? Oh, I don't see that. You don't show the orange line. Okay. Got it. It's under the blue line. It's not on the same line. Okay.
What I should do? Yeah. Sorry. Yeah. So and here we see the errors is bigger, but they're still kind of matching. Here they're a bit different in the beginning, but they again match. So this is an interesting observation. However, it's interesting, but it's not very instructive in our model because it just means that.
Are you sure it's not flipped isospin and charge here? Because isospin should match, but isospin, which is protons, Agakitazawa, should
Right.
match baryons.
Exactly.
No, but okay.
No, the next one.
Abstract ratio.
Dark ratios. Yeah. Yeah, you sure the labels are not?
Maybe they're normalized when I'm thinking about it. So you have the pink line,
Yes.
and if you divide it by the same number with other lines, you would obtain the lower result naturally.
No, not the same number. You divide by number of protons. Right.
So I guess it's probably then it's
No,
only
I think
normalized.
it's just the axis. The
Okay.
labels are
The
flipped.
labels are mixed.
Color, I guess. Then.
Yeah.
Okay, yeah, I would check it. I think I understood, but I need to check it. Yeah. Sorry. Yeah. Now we're going to the more realistic part of my research because, as I said in the beginning, when I talk about the experiment and the theory, when we have the momentum space in the theory, it's something interesting because it's something that relatable to the actual experiments. Since it's harder to observe the coordinate space in the experiment. And this depiction is simple picture of this alpha cut, which I showed before, which you can perform it in coordinate space, so we perform a cut in z direction, or in momentum space, so we perform a cut in the direction of pz, or the momentum along the x. And here is our standard cumulants for the momentum space, which means that, and it's important to notice that alpha here is already a different thing. You cannot define alpha here as, the part of the box, because in the momentum space, the box is integrated out efficiently. Some theoretical results, which we extended from the first article, gives us these formulas for the ideal gas in the microcanonical assembly with energy conservation. So this is what we expect to observe if there are no interaction. And as you can see here, in ensemble average molecular dynamics, our lines inside of the error bars, matching these ideal gas trend lines, which means that if there is a signal, it's too small to observe. Now, it appears the question, how we can correlate two spaces, momentum and coordinate space?
What do you mean the signal is too small to observe? There is no signal.
Yeah, but I mean, it's too strong words for me to say.
But that's what it is.
Yeah, but I agree with you.
Yeah.
If it's match ideal gas lines, then it means that there are no signals at all. And the good thing is that now it's a good motivation for us to study the way we can correlate the coordinate momentum space, and we can do it in many ways. But what we are doing now is called the collective flow, and collective flow in form of Bjorken flow. So basically, we modify our momentums of a system to give them direct correlation with the coordinate, as you can see here. It means that our phase space would deform like this, and our acceptance also would deform, which is important because our acceptance now, our alpha, is dependent on the flow. And you see here that basically we just make this boost with coordinate relation, if you wish, to the velocities or to the momentums, which consist the thermal part gained from the statistics of the molecular dynamics, and the collective flow part, which is our phenomenological boost with the constant kappa, which can be mapped to the collision energy, and that's how it can be connected with some, let's say, real values of kappa, because of course, without it, you can do kappa 1 million and get nothing. So kappa should be reasonable. And yeah, we choose these parameters, which are inspired from the, again, heavy ion collisions. Here we can see our results for the standard cumulants, not corrected standard cumulants, just again because correction would give you the infinity. And you see that with the increasing of energy, you would get from this result, which is the result of the ideal gas, red line, and also red band. Red band corresponds to our no flow result, and again it matches the red line. And with the increasing of the collision energy, which means the increasing of the flow, we get into the coordinate space result. So these lines, which you can see here, is best to see it on kurtosis. It's already for even 2.4 GeV, a very, very negative result compared to the ideal gas case. So So it's -9 instead of -1. And of course, then once we increase the collision energy, we're getting slowly to the coordinate space result. And then if we would increase it more and more, it would just be around the coordinate space result. It won't change too much if I would do 10,000 of the GeV, for example. So this is something that interesting, but yes.
Is it still in the box?
Yes, I mean
Is
so
it special?
what we're practically doing, we have the statistics as I show here. Yes, we have this part, external part, we gain it from the box statistics, and then we boost them with the collective flow part, which is phenomenological boost. So our system now is expanding, but it's not the expansion in sense of, I don't know, some transfer model. It's expansion in the sense that we just do, yes, Bjorken flow expansion.
So you have the periodic boundary, right? So which means that the particle getting outside on this side is having inside function.
No. So we have the center of mass, and compared to the center of mass, our particle goes to the left and to the right with the given flow kappa.
So you take your box with the particles, and then you take a snapshot, right, at a given time, for instance, right? Or at the end when you're done. And then you look at the C coordinate in the box, and the larger the C coordinate, then you take the particle and boost it. In the C coordinate, the non in the C direction, the 3 direction, right? And you just take these particles in the box, and the more further it's out, the more you boost it out. So there's no evolution; you just do it by hand. It's exactly in this little figure there, right? I mean, the higher the particles are in the vertical direction, this is the C direction in coordinate space, the more they get boosted out.
Yeah. Okay.
This is like more collective motion, not collective flow.
Whatever you want to call it.
Well, collective flow is literally.
I mean, the box is the wrist, right?
You start with the box and rest, and then you just add this flow on it. We don't motion. We don't evolve something or do connectivity with hydro. It's just done by hand.
So worth noticing that in principle our system not interact once we stop the box simulation. So our flow part, they are essentially have no interaction between the members of it.
So is that purely kinematic effects?
I mean, but collective flow does that for you, right? It's just so that all of a sudden you get a space momentum correlation, as you can see in this plot, right? And then you all of a sudden, by measuring momentum space, you're actually sensitive to coordinate space, where the physics is.
I think I didn't really fully understand. So you have so the Z direction, right? And then if you have a particle in the large Z direction, then it's boosted.
Yes.
And
The
then,
fastest one, yes.
yeah, but you have the finite boundary, right?
No, the boundary is gone.
It's gone.
I mean, we stop the calculation, and now we have particles sitting around here, right? So we stop the particles,
It's alpha,
right? And so now we are done, right? So you have these particles, and then you look, and this is your C direction, let's say. Well, let's like this one. So if the particle has a large C, then it gets a big velocity, and the small C gets a small.
What do you mean by boundary is gone? Like you don't.
I mean, we know all we need then to know is the momentum.
Okay. So you don't have to. I see.
Yeah, practically we got this from our box, and there are no more boxes in this part.
Right.
We just have a table which we boost and then study statistics.
Okay.
Yeah. So molecular dynamics is just a way to prepare a local rest rate
Exactly.
state, which is already in terms of particles.
Yeah, but it carries the information, gives information.
I'm still confused. I thought you were doing molecular dynamics,
Yeah.
some temperature and looking for equilibrium.
Yes.
Now, how is this energy scale, the heavy ion collision energy comes into play? How is that?
Through
What
the-
parameter?
Through the constant kappa. So constant kappa,
What is kappa?
it's a phenomenological constant which defines how strong is our flow. So
Where does the flow come from? You put it in by hand?
Yes.
yes,
That's kind of start. So basically, you have coordinate space, very nice result. Use the flow.
Yeah, but this is of
Take it
course
out in the
a cheap way out, right?
Yes,
In principle,
it is.
you would have to do the full calculation, right? I mean, but this is the first way to see if I have a chance to see something, because at rest we don't see anything, no effect. Right?
Yeah, and worth noticing that this flow is good for the high energies. That's why, for example, here you have such large result for small flow, because it has some limitation of usability, I would say. So it's not that we say that it's what you would obtain in the collision with real flow.
If you go to higher energy, start at 20, if you go to 60, 20, well,
Yeah, as I said, we will just reach the coordinate result.
okay.
The result which I show here. Yeah, here. So we'll just reach this result. Okay, so here you can see the factorial cumulants, again without the correction for the global conservation. And as it was shown before, they are just with increasing of flow reaching to the coordinate space values. Worth noticing, in my opinion, the kurtosis thing, because you can see that first it's going up the green line, and then it changed the monotonical behavior to non-monotonic behavior. So here you have just the up green line just above the ideal gas result, then it's start to curving, and here at the 7.7 GeV, it's already have a large gap here. And again, of course, you can build this plot for the proton conservation thing, but it's something very I didn't manage yet to do it, but yeah, it also works for the proton charge conservation case. Here you can see the, again, standard cumulants, and here I rather build them for a given acceptance in the momentum space, which is 0.5, as you can see here, and I just do different boost as a function of square root of s. You can see here that they are quite large deviate from the red line. Red line is what is expectation of the ideal gas at given alpha. Because as I say, alpha, the symbolic fraction, dependent on the quality flow parameter or on the square root of s. So this red line basically show you the ideal gas baseline for each energy. But yeah, to compare it with our lines, which actually corresponds to 3 different densities. And you can see that our signal is quite large for these two, for the small and critical density. So it's hard to distinguish them, but it's dramatically changed in the kurtosis. In the kurtosis, we have this large gap around 10 GeV, and it's easy to distinguish it from the other two lines, basically large density and small density. However, interesting to notice that this red line, which again ideal gas, already show you this small gap here. So it just seems to be that interaction increasing the effect which already is there, and basically which is just behavior of kurtosis with this changing of alpha with the increasing of energy. So just to make a comment, alpha with increasing of energy is falling down, but very slowly. So at infinitely large collision energy, alpha should reach 0. So it should be no particles in the acceptance. At least, I mean, it follows from our model. Of course, I'm not arguing that it happens in the real world. Here you can see the factorial cumulants in the same plot. So it's again square root of s. And they shows interesting result in the sense that you can observe that they deviate from the red line pretty much, but unfortunately, absolutely the same what we saw in the previous plot, pink line, which is isospin optimization, it reaches the red baseline of the ideal gas, so there are no more signal here. But it's not that bad because, again, first of all, the blue line, the full baryonic system, is very, very, very much non-Gaussian, and also because this orange line with this charge conservation for low energies is also quite different, at least factorial cumulants, from the ideal gas. So factorial cumulants do not show a strong signal for the protons, but still I think that it was noticing that it deviates from the ideal gas, which is a nice result. To sum it up, we perform a study of our molecular dynamical system with Lennard-Jones potential and high statistics to find the factorial and standard cumulants up to the fourth order. We checked scale variance, skewness, and kurtosis in the coordinate space, found that they are very, very much deviate from the ideal gas case, but in the momentum space, the interaction is vanished out. We also checked the factorial cumulants, and which uncover the n-particle correlations, and high and low energy regime for the proton factorial cumulants shows different types of suppression, but both show a quite huge suppression of the signal critical point. Finally, we studied the momentum space fluctuation with the collective flow, which gives us the connection between the momentum and coordinate space, and these correlations, which we have now, recover the signal in the momentum space, which means that, again, in the future, we want to prolong the studies, implement the more realistic version of flow, by starting from the elliptic, spherical, and maybe more realistic at all. Also, that we want to implement multiple components in our molecular dynamics, think how to do it. And also, one kind of working now is that we might try to work on the critical point search with expansion scheme, which was discussed here a week ago by Hitachi, using our real Lennard-Jones equation of state to check if it works there. Thank you, and I hope someone would have questions to me.
Yeah, what is the computational scale of such 2 million events? Do you need many computers? How long it will take?
Practically, I can say direct numbers because I did it last week. Not for this, but for other point. I did 14 nodes, 7 nodes, 2 parallel sessions on each node, and it takes 1 week to gain 2 million events. So it's not that terrible. I mean, I obviously I can do like 4 million events like this, or I can do just not 14, 28 nodes.
So it's 14 GPUs.
Yeah, but I have 2 sessions on each one. No,
7 times 2, right?
Yes.
14 GPUs. Which one is it?
Sorry?
Which GPU?
No, I don't remember.
I think it's GT and NT, if I remember correct. And it's a single precision.
Yeah, it's
one
single.
numbers.
So I got lost when you said implementing the Bjorken flow recovers the signal, right? And then, but I was thinking if you like have a particle and then it's boosting into the one direction, it's kind of they are getting less interactions, right?
Of course they are.
Why
here,
we do have like more?
I can explain it. I can explain it. So the reason for it is that if we want to see the interaction in our system, not in real collision, important to say, we need to observe somehow the coordinate space. Because in momentum space, by the construction of our system, there are no interaction. Our potential is only coordinate dependent. Once we do the collective flow expansion, now our momentum is connected with coordinate. So each z momentum of each particle have also z coordinate. And that's how you can have a connection with the coordinate position of our particles. And you can see it here against a good picture here. Yes, so that's what happened now. So now our particles are correlated both in the direction of z and pz. So mathematically speaking, I mean, this also makes sense in the sense that that's what happened in flow. Like when you have the collision is again quite. Yeah, I think it's basically the best way to see it is just to understand this picture well and compare it to these two pictures, right? So what we have in momentum space is this. So now whatever we have in Z, whatever information is just integrated out. And here there are no connection with momentum. And now we connect them. So more and more flow, more and more involved Z dimension becomes.
The connection I understand, but like if you prepare some particle, let's say at the zero momentum at the initial state, and then if you just let them evolve with the Bjorken flow, it's basically the straight trajectory, right? And then they wouldn't like collide or if
Yeah,
with
that's
a
why
short range and
we
it
say
wouldn't
that.
collide, and then like it's same as the.
That's why we say that our system is thermalized, so it's already interact inside of the balls, and then once we boost them, they already carry the information about interaction, but they're not interact afterwards.
You wait until full thermalization before measurement. Yeah.
In this case.
Okay, yeah, so by construction, you can do whatever time you wish to do the boost. The only difference would be that since, for example, here the signal is smaller, yes, the effects would be suppressed additionally. So yeah, I can do it for non-thermalized system, but then it appears the question like which time scale you need to check, you know, which would be the true time scale to compare with energy data.
This is equilibrium scenario, right? It's
Exactly.
the best possible.
Right.
No, it's not the best possible, it's the one which like
It's the best possible.
Because your sequences are smaller,
Yeah.
otherwise.
okay, so the best like the strongest, yes.
Further, yeah.
Have you seen about implement in a realistic hydro simulation? Hydro.
That's what I'm thinking about doing right now.
There are no
But
particle.
there are a lot of problems in it. If you wish, we can discuss it because it's very interesting, and that's something that we discuss with the postdoc of Volodymyr, if it's possible to do. Gregoire, yes. He said that yes, he thinks it's possible, but it's some kind of pain to do it.
What do you mean?
Well, for example, I have the Cartian time. I don't have any relativistic time. It's already a problem. So yeah, we need to map somehow. Also, we'll have the problem that in hydro you don't have the conserved charge, for example, and I have. But yeah, it's something that would be interesting to do.
All right, another stupid question. So, has anyone thought about how to actually translate coordinate space information into your final measurement? You at the beginning you say there's no way you can do it. Anybody working on that direction? I mean,
Maybe I didn't understand the first place.
So-
Sorry.
you say that theory working on the coordinate space and moment space, but experiment only working in moment space.
Yeah, I
Can you
heard-
translate some of the coordinate space information into some observable
Actually,
space? What? That's what I'm thinking.
Yeah, I've heard about it. I don't know how they do it, but I heard about it. People try to do it.
Also, in the live nuclear production, you send to the coordinate distance at quantum distance.
That's sure.
We'll do Cooper Fridays and endpoint correlators.
I remember, I mean, again, this is kind of really naive, and I still remember what's like, and who haven't, at that time, Dima and Koch, and this very interesting paper say that suppose you have a significant bulk viscosity, you will have some observables. You know, I mean, they were thinking it's very simple when you have phase translation, right? I mean, phase translation is local in their kind of argument. So that means that you translate some of the coordinate space information into.
Yeah, but what the mechanism of the transfer is just.
So nobody has thought about it, or maybe it's dead end.
I mean, as Sven been said, I mean, one thing what is being discussed a lot is the light nuclear production, right? So if you have a low correlation, then you can pick it up if you're lucky, right? I mean, and then you can do this femtoscopy, but this is very long range stuff you can see.
Then you need many events or.
No, but you need to make like Nu does for his whatever.
I know, but if I want to do something like this, like cumulants, is that
Well,
possible?
no, then it doesn't come out of femtoscopy. Then you have to. Right? I mean, well, it's very simple. The experimentalists need a better detector that they can measure on the Fermi scale in coordinate space, and that's all. And then you can do it. No, just joking, of course.
You just look at star data. But yeah. So yeah, so this is the null result, right, of BS2, as
Right.
sometimes is interpreted. But also, so like kappa forward, kappa one, for example, right, looks like consistent with 0. But if you show your result in 24th slide, maybe for instance, let me go there. So in 24th slide, this is the best scenario equilibrium near critical point. And when you go to protons, so the purple band, you get the same null result after everything is said and done.
I see.
So maybe the expectations were a little bit too optimistic in the first place, and not necessarily the start ruled out critical point or something.
That's the point is that this very interesting to study the factorial cumulants because they show very good way of suppression.
And they also show how much maybe better things would be if they could measure baryons in their full glory.
I mean, that's what I'm trying to get at. If you find some, I don't know. Okay, forget about it.
Okay, let's thank the speaker.